Hello, I'm Prismatic, and today I'm going to be showing you some advanced Kinect rendering techniques in TouchDesigner. So there are two main techniques I'm going to show. One is using instancing to create this sort of statuesque look on the right, and the other one is using this technique I call direct rendering, where instead of instancing geometry, we are just directly using this texture data to render within the fragment shader of a material. I'm going to explain that more in depth later, so don't worry if that doesn't make sense for now. This has some real advantages over instancing. It's a lot more efficient and I think can create some much nicer lighting. So here's a little outline of what I'm going to cover in this tutorial. First, we're going to access the Kinect data and isolate the subject. And I've also got this working with the Kinect V2. It's a little grainier, but just to show that you can still do that. Then we're going to show how you can use instancing to create this sort of statuesque look on the right. Instancing is sort of the classic method for rendering Kinect in TouchDesigner, but there's some subtleties and differences to create this sort of look that I want to cover. Next, I'll get into direct rendering to create this metallic look on the left. That's really the heart and soul of this tutorial. That's what I'm most excited to share. There's also depth refinement, which is this component here, also very important. If I turn that off, it gets really grainy. So I am filling in holes, removing speckles, and smoothing the data to create nicer lighting. Finally, I'm going to cover how you can add shadows to this direct rendering method, which involves some hybrid rendering. Before I jump into it, I do just want to mention that we're going to be writing a lot of GLSL in this tutorial. So if you're not familiar with writing custom GLSL, this might be a bit on the trickier side, but I'm going to post this project file so you can also just download and follow along there. All right, so let's get into it. I'm going to select all and delete, and we are going to recreate this from scratch. So first I'm going to add a base. Let's call this Kinect. I'm going to create a Kinect Azure top. I like to mirror the image. So for this tutorial, I'm going to leave it at the default narrow FOV. You could also switch to this one, wide FOV 2x2 bend, and get more of a fisheye angle. I'm also going to create a Kinect for the V2. Again, mirror image. With this one, I want to select the depth point cloud. So now let's do the Kinect Azure select. You have to drag that in, mirror image, point cloud is what we want. When you're isolating the subject from the Kinect, there are kind of a few different ways you can do it. You can use the depth map and just threshold based on depth. Or, if you're using Kinect V2, there's also like this player index feature. But I have found that the best way for me to do it is to use the point cloud data and to threshold based on XYZ position. I'm going to close this so we have some more room to work with. This is a technique I learned from this interactive immersive HQ tutorial. Shout out Albers on this one. First step is creating a point transform top. We want to view this as points from the front. And you can press Q to turn off adaptive homing. What we want to do is basically set this up so that it will be easy to threshold. This is a little bit more relevant when you're working in a bigger space and not close up. But what you can do is transform it up and rotate on the X and Z axes until you get sort of a nice straight line here. And then you want to bring this up so it's right below the ground. This tutorial covers it in depth, so I'm not going to go too much more into the reasoning of this. Now what we can do is create a GLSL top, and let's just edit this pixel shader. I'm going to create a few uniforms to start. U X bounds, U Y bounds, and U Z bounds is what I want here. These are all going to be vec2s. And I just use U at the start of uniform names. It's kind of convention, so you know you're working with a uniform in the code. So let's create that over here. U X bounds, duplicate that a couple times. So now I want to sample this input, and I'm going to call this position because we're working with point cloud data. What I want to do here is basically threshold the position based on XYZ. So I'm going to create another uniform here called vec3 u out of bounds color, u out of bounds color. All right, so we can basically just do one big if statement here and say if position.x is less than u x bounds.x, or position.x is greater than u x bounds.y. So this x and y are basically representing the min and max values that I want to accept for the x position. And for that, we'll then set the position.xyz to u out of bounds color. So now you can see this working. If I change the min and max of x, you can see that we are thresholding and setting anything outside of those bounds to this u out of bounds color. Now we just need to do the same with the other variables. So position.y, we're going to set that to y bounds, position.y. Okay, now we have nothing. Let's change these bounds a bit. Maybe -1 to 5. Yeah, all right. So y bounds was the issue there. So what you can do now is, set y bounds to 0. And because we nicely set this up, everything on the floor is going to get cut off. And you can then set up your z bounds to kind of cut off everything that's farther away from the camera. All right, so this is working okay, but you'll notice that there are a lot of these strange green points popping out, and we haven't really isolated the subject in the way we want to. That is because there are a lot of unknown point values in this original data that get set to 0, 0, 0. That's what's creating this strangeness. So in order to fix that, I want to plug this in as a second input. We don't want to use the point transformed version to check if it's an unknown point because those values have changed. What we can do here is sample the original and say original equals texture of S. I'm just going to copy this 1, and we can add something here and say if original.xyz equals vec3 of 0. What's our issue here? Wrong operand types. Oh, needs 2 equals and no semicolon. So now we've got something looking pretty good because we're checking if the original value is out of bounds, and we're also thresholding based on the XYZ position, and we've got a nice isolated subject here. So I'm going to create a null here, call this null isolated, and wrap this up in a base and call this threshold position. So I just want to show if you wanted to use this V2 sensor, again, we're using the depth point cloud. You would need to do different thresholding because this is in a different position. That's kind of the downside of this method, is that every time you change the position of the sensor, you need to redo this whole point transform and thresholding process. But it's not so bad. Usually just set up your camera in one spot. You can do this for the whole night and then go from there. So for the sake of this tutorial, I'm going to keep using this Kinect Azure that we've already got set up here. All right, so now we've got this nice isolated XYZ subject. The last thing I'm going to do is add a chroma key here so that we can get an alpha channel. I'm going to set the value to be 0.001. And now we have this alpha channel that says whether we are inside of the subject or not. I'm going to create an out here, and we have completed step 1. Isolating the subject. Now we can go on to instancing. I'm going to create a base here, call it instancing. Don't need this out. I'll just disconnect it for now. So what we're going to do is instance some geometry. I'm going to create a box, connect it to a transform, and let's do a geo here. I need a camera, a light, and a render top. And we'll plug this in here. So now we've got a basic rendering setup. Now what we want to do is set up instancing. I'm going to create a null here with Alt-N. This is just good practice in case we want to do anything with this position data in the future. Go to the instancing tab, turn on instancing. I'm going to set the default instance op here. Let's turn the scale way down to start, and now set this to R, G, and B, and you can see our point cloud pop up. I'm also going to add active A, and that's going to help a lot with cook time because we're not dealing with any pixels outside of the person. All right, it's pretty off screen here, so I'm just going to adjust the camera so it's more in view, and maybe we'll increase the size of it a bit so it's more visible. All right, so this is the usual approach that you'll see in Kinect rendering tutorials, where you just take the straight up XYZ position data and use it to instance geometry and then, finesse the camera so that you are looking in the right spot. I don't like this approach for a few reasons. One, it's hard to set up the camera properly. It looks like this point cloud where it's really obvious that it's not actually a real 3D object. And it's also really hard to align it with other things. Like, if you come up with colors based on this position data, it's really hard to then take this instance image and composite it with anything else because it's not aligned. I want to show you this basic instancing setup to show the motivation for the next instancing approach that I'm going to show you, which uses an orthographic camera, so it's perfectly aligned with this input texture. And I think it looks a lot nicer for most use cases. So in order to do that, the basic idea here is that I'm actually going to throw out the XY position data from this point cloud and instead just use the XY of screen space position and only use the depth from the Kinect point cloud. It's going to make more sense in a bit. I actually don't want this XY position anymore. I'm going to use a reorder top here to set the red channel to be blue. And I'm going to set this to be 32-bit mono. So we kind of throw out the rest. But I do want this alpha channel. So I'm going to set this to 32-bit mono plus alpha. Now we've basically just isolated the depth map. So the instancing is no longer going to work. I'm going to create a new base here called instancing position. And also I'm going to go in here and split the viewer left and right and set this to be top viewer and turn on display here so we can start to look at this more easily. I also want to set the resolution of this render top. Let's create a little custom parameter for that. Just drag and drop, bind new pars master, and create a null here. Call this null position. And I want to set this to be the width and height of that input. So now we're sort of set up to view this instancing as we fix the position data. Okay, so what I was getting at earlier is this idea that we're replacing the Kinect XY data with screen space XY data. So this will be perfectly aligned with the viewer when we instance it. So I'm going to create a ramp top, create two ramp tops. One is going to be horizontal, representing the screen space X position. The other one is going to be vertical. I'm going to create a reorder top here, and we basically want to create XYZ position data. X is going to be ramp 1, which is input 2. Y is going to be this vertical ramp, which is input 3. And then Z is going to be this input depth data. So that's input 1, red channel. This isn't quite right. This needs to be set to 32-bit float RGBA. And now we should have this nice position data. So we can view this as points and get a nice image of the point cloud we're working with. So what you might notice is that this is reversed. That's because of something particular about TouchDesigner. Basically, its Z-axis is flipped from most other 3D software. And as you get farther away from the camera, it's negative. Whereas in the Kinect data, when you get farther away, the depth gets larger in the positive direction. So in order to fix that, it's a really quick fix. Just add a math top here and multiply by -1. Now this is kind of what we're looking for. You can see it pop up here. Doesn't look good for now, but we'll fix that later. So there's one other subtlety here, which is that this is actually a little bit smushed. It's smushed in the X direction, and that's because both the X and Y position data here go from 0 to 1, but this is not a square. This is 640 by 576. So it should actually be stretched out a bit in the X-axis. Hopefully that makes sense. The way to do that is to basically do aspect ratio correction. So I'm going to create a new constant here. We'll call this aspect X and aspect Y. And there's a little expression to figure this out. Op_in1.width over the min of the width and the height. And then for Y, we'll do the same thing, but the start is op of in1.height over that. Basically what this is doing, it's saying the minimum axis in this image is going to be 1, and the larger one is going to be some value larger than 1 that represents that aspect ratio. So what we can do now is create a math here and use these values to rearrange the X and Y position data. So now if we look at this output as points, this is actually properly distributed in space, and it will adapt to whatever resolution of Kinect data you want to use. Okay, so now we've got this nice position data. Now we can reconfigure this instancing setup to kind of render it in the way that I want. So I'm just going to create a new camera to sort of reset that. And we want to set this projection to orthographic. Ortho width should be 1 and ortho origin should be bottom left. It looks all white, so we got to fix that. I'm going to create a new PBR matte and set that as the material here. With the light, I'm going to zoom in and try to kind of hone in on the geometry. And I'm also going to turn the dimmer way up to like 12. Where you'll really start to see it is by turning on shadows. So we're going to use soft 2D mapped. I'm going to set the light size to 0.1, set the max shadow softness to 0.02, and that starts to create some decent shadows here. I want to bump up the resolution a bit, so I'm going to multiply these by 2. Also, I want to fix the scale of these cubes. So we can kind of dynamically determine the right size here by referencing the input. Op null position dot width. We want to do 1 over that. That's going to make it so that each box fills up 1 pixel. I am going to create a custom parameter here called point size, default 1, max 2, and multiply by that part point size so that we have a little bit more control over this. I find this value looks good around 1.2. So it's looking pretty good. We have lost some detail in the face depending on the angle. One thing that can help a bit with that is to rotate the boxes a bit. So I'm going to input this to set the resolution, but we really just want noise. And turn off monochrome and bring the amplitude way down to maybe like, 0.02. I'm going to call this null rot 2 and pass this in here, RGB. And that just adds a little bit of definition to it because not all the boxes are facing the camera. So yeah, this is the basic effect that I was talking about. There are some nice advantages of this technique over the traditional instancing method. One is that this actually looks like a 3D object. You can't see the edges of it because it's pixel perfect. You know, every pixel in the output has a corresponding input pixel. The other thing you can do with this is composite it with other textures. So if I bring this in and just create some funky colors based on the depth, I should be able to multiply these two. Okay, these are a bit off actually, and that's because I forgot to do something with this ortho camera. Our ortho width, we actually want to be aspect ratio corrected. So it's parent.par.resolution 1 over parent.par.resolution 2. So now that's perfectly aligned, and you can start to get these interesting looks where you have color and really nice shading and shadows from this instancing. I also want to mention this render can be cleaned up in a variety of ways. You can see there's sort of this weird edge around it. There's a couple artifacts over here. I'm going to address that in the depth refinement section, so we'll get to it. So this render looks pretty good, but conceptually it's a bit strange because we've basically recreated a texture operator where we're taking in this position data and we are shading it, and it's a 1-for-1 mapping. But in order to do that, we are instancing geometry for every single pixel instead of just working with pixel data. So this is quite expensive. It's like 8 milliseconds. And this just got me thinking, could we just render this shading and shadows directly within a texture operator instead of instancing geometry? So that is what this new direct rendering method accomplishes. So let's get into it. The first step here is I'm going to create a new base called direct position and normals. In order to shade a 3D object, for each pixel, you need position and the normal. The normal vector indicates how the pixel is oriented in space. And once you have position and normal, you can kind of just use the normal lighting functions and it should look good. So what we need to do is calculate normals from the position data. In order to do that, I'm going to use this tool from Packeta 12. You can find it on the derivative forum called normalmaps.tops.tox. All right, so I've got that downloaded. I'm going to drag it into the project. I want to plug in this position data. This doesn't look great yet, and the reason for that is we need to go in here and change the source of the normals to be blue, which is the depth in this image. And now we've got pretty nice looking normals. There are a few things we'll fix about this later. There's kind of a weird edge here. That will do for now. So I'm going to create another out here and come back up. Let's just create a couple nulls here to see what we're working with. Null direct position, null normals. So I want to create a base that is going to take these two in. So I'm going to create a couple ins here and pass these in. And again, I'm going to create null position and null normals. All right, so before I continue, I'm noticing that something is a bit off here and that this alpha is -1. So I need to go back and fix something. This math should not be affecting the alpha channel when we were reversing. So I just need to go into these two and turn on that alpha channel mask. And now we've got what I'm looking for, where the silhouette has an alpha of 1, the outside has alpha of 0. Okay, so we've got this position and normals data. There are a couple ways that we could go about creating a shader to work with these two. One would be to create a GLSL top and plug these in here and write this fragment shader and just sort of implement a custom lighting function that takes in the position and normal and calculates the shading. But there's another way that I want to do this, which is to use a custom GLSL material and basically hijack the fragment shader of the material by using this position and normal instead. And that way we can use the custom lighting functions that are available in the material shaders. I'm going to explain that more in detail. To start, let's create a grid SOP and a geo and a camera and a light and a render top here. I'm going to set this camera to be orthographic, ortho width to be 1. And now we've got this grid SOP that is filling the whole render. I'm going to move this over here. I'm going to create a PBR mat and output this shader. And let us use this PBR GLSL top as the material. So what we can do here is basically use this pixel shader like a GLSL top. We don't actually care about the geometry that's going into this geo. I just used a grid to fill the whole screen so that each fragment is going to be rendered. If you're not super familiar with the graphics pipeline, this might be a bit confusing. Here's what the general shader pipeline looks like. You have vertex information, you run a vertex shader. Optionally, you can run these shaders. There's some more internal processing, and then you have your fragment shader. In TouchDesigner, the GLSL top is a fragment shader, and that's how all texture operators work. They are fragment shaders. Something to know is that you can't just run a fragment shader. You need geometry to fill the screen, and the fragment shader is only going to run where there is geometry. All of these texture operators are actually running this entire graphics pipeline, including a vertex shader. It's just not going to be doing anything interesting. It's much like this. I would guess that something very similar to this setup is happening behind the scenes for every texture operator, where you fill the screen with the simplest geometry you possibly can, and then you just use the pixel shader to render. This is a very common technique. If you go to Shader Toy, which is an amazing site for fragment shaders, that's how this is working. On WebGPU, it is rendering two triangles that fill the entire screen, and then it's just using the fragment shader, and it's not actually referencing the geometry at all. Okay, the other thing I want to mention at this point is that when I was using TouchDesigner for the first few years, I didn't really understand what a material was. I thought it was somehow this sort of magic thing that shaded 3D objects. Really, all a material is a shader program with extra data and functions passed in that integrate it into the rendering pipeline. So it's not really that different than using a texture operator or a GLSL top. The differences are that you have access to the vertex shader part of that program, and that, again, you have extra data and functions passed in. So you have access to any lights in the scene, you have access to geometry, and you have access to lighting functions. Like if we pull this up, you'll see we have this TD lighting PBR function. I'll just show you, if we try to run that function in this code, I don't know what it returns, but we'll just do that for now. This should say no matching overloaded function found. This function doesn't exist in a GLSL top. It's not exposed. So there are a lot of extra niceties that you get within this fragment shader versus this fragment shader. But again, I just want to emphasize this. They're not really that different. And you could do whatever you want in this fragment shader. It doesn't have to involve the input geometry. So what you can do is basically hijack this material, use the input data and functions, but just use it like a fragment shader and completely ignore the geometry and vertex. So that's what we're going to do here. If you want to learn more about these specific data and functions that are passed into this material shader, you should really read this page in the docs. Okay, so I want to create two samplers to start with. We're going to call it S position and S normals, and we're going to pass in these two inputs here. I'm also going to delete this GLSL top. So now I'm going to open the pixel shader and declare those uniforms. Uniform sampler 2D S position and uniform sampler 2D S normals. So the basic idea here is, instead of using the position and normal from the geometry, let's just sample those things from these samplers instead. So in order to do that, we need a sample position, and that's going to be glfragchord.xy over u resolution.xy. This is going to be a new uniform that I'm going to pass in. Uniform vec2 u resolution, and let's set that up on the vectors page. This seems like a good time to create a resolution uniform. I'm also just going to rename this and call this direct rendering. So customize component, let's go to the common page and drag resolution up here. And I'm going to set this as we did here, so it's related to the input. Okay, now we've got that resolution set up. Let's just hook this up to our resolution uniform. Now I'm going to go into the shader and let's see if this sample position is working properly. So the way to output in this fragment shader is with this line here. If I come up here and let's set the color to be sample pose 0, 1 and just return from there. Great. So this is sort of the classic UV coordinate map that we should be expecting, which means that we can now use this to look up the position data and normal data for each pixel in here. All right, so now that we've got this sample position, I'm going to go ahead and sample our two textures. So position sample equals texture of S position sample pose. And we'll do normal sample S normals sample pose. To make sure this is working, let's just pass in our position sample here. Nice. So I want to extract the actual position and normal from here. Say vec3 position equals position sample.xyz, and vec3 normal equals normal sample.xyz. This is going to cause an error because normal's already defined here. So let's just get rid of this as well as world space norm. And we need to remove everywhere that is used. So I'm going to delete this part. We don't really need it. Now we should have no problem there. We need to adjust this normal a little bit. And that's because if you look at this input texture, the way that the normal top works is that it's normalized between 0 and 1. So on the left side, the R value is going to be close to 0, but that's not actually accurate for how a normal should work in world space. On this left side, it should be -1, right? Because it's pointing in that direction. So we just need to kind of compensate for that and say normal equals normal times 2 minus 1.0. That's going to shift it, and let's plug that in here to kind of see what we're working with. So now you should see, oh, we need to change the pixel format. Let's go 32-bit float RGBA. That will allow us to have negative numbers. So now you should see, we see a -1 on this left face. The other thing that is good to do is just normalize it in here to be sure that it has a length of 1. I think it probably already did, but it can't hurt. All of this math is expecting a normalized vector there. Okay, so now we just need to use this position and normal throughout the code in our lighting calculations. And it's really just one change, which is going down to this lighting method and putting in position instead. So this is actually should be working properly. I think that it's because our light is too dim. Yeah, all right, so now we start to see it. I'm going to zoom in here. It's a little bit weird because you can't see the actual geometry. You're kind of like guessing where the light should be. But yeah, you can start to see the basic idea here, where we are now using a PBR rendering method that integrates with the lighting and the camera and such by just passing in our position and normal instead of using the geometry. So there's a quick fix I want to do here, which is to get rid of this background, and that happens up here. I want to say if position sample dot a equals 0, I want to basically bail early. So we're going to set this equal to 0 and return. Now the background disappears there. I'm going to create an out here. And now we've got something that looks very similar to our instancing setup. But if we come out here, the GPU time here is 0.2 versus 8 milliseconds here. Massive difference. And we can start to play around with this more and get some cool effects that you can't really do with instancing as well. So I'm going to turn the viewer on for this out and take this viewer panel into direct rendering instead, so we can start to work with just this. So something pretty fun you can do with this setup is to add an environment map and get some cool reflections. So in order to do that, I'm going to go to Polyhaven HDRIs. If you don't know this site, it's a great resource where you can download a bunch of HDRIs that you can use in any 3D modeling software. I am going to use this warm restaurant night. What do we want here? Yep, HDR, 2K is fine, and download it. And then I'm going to drag that into TouchDesigner. So now that we have this, we can create an environment light and give an environment map. Okay, so we've got our environment light. It's not really looking as expected, and that is because we need to change the parameters here. So I'm going to bring roughness way down so we can start to get some reflections, maybe like 0.2. Yeah, now we've got the basic effect. It doesn't look very good yet. Let's turn this light down a bit to 4. And there's something else that's really important that is missing here. This image is in linear space. That is how PBR rendering works, is it's expecting linear input and it outputs in linear space. And when we actually display an image, we want it to be in sRGB space. This is a whole topic that's kind of beyond the scope of this tutorial, but there's a quick fix for it, which is to use this math top and turn on this toggle here. Convert outgoing linear to sRGB. And this is actually going to be much more accurate in the end. I want to turn down this dimmer a bit as well, and maybe turn down the environment dimmer a bit, and maybe we can get a little bit warmer lighting here, something like that. Now this is starting to look a little bit more like the gold statue look that we're going for. If you want to learn more about this whole distinction between linear and sRGB and how to work with it in TouchDesigner, I highly recommend checking out this post from Lucas Morgan. This is where I learned about this. So it's a really important part of the PBR workflow that I think doesn't get talked about enough. All right, before we go further, I'm just gonna add a couple of things here. Let's add a constant to give kind of a black background. Set the operation to under. And I also want to add some bloom. Bloom is a really important effect. Doesn't look good right now. Let's fix this up a bit. Bring the bloom intensity down, max radius down a bit, maybe gamma down a bit. Yeah, it's still kind of intense. All right, that seems about good. Here's without, here's with. Really, anytime you are rendering a 3D scene in TouchDesigner, and especially with something shiny like this, you should be adding bloom, because this is an effect that happens in real life. There's basically a diffusion of bright spots, and in order for the scene to look accurate, you need bloom. It's almost as important as adding shadows. So yeah, I just want to emphasize that you should be using bloom. So we've got a decent looking render here, but it's pretty noisy. It would be nice if we could smooth the surface, if we could get rid of these sort of weird speckles, and also if we could fill in any holes. You can see if I move my hands especially, or even if I just create some distance, so there's like this halo of black pixels. Those are unknown pixel values, and these are things that we can fix in real time. So that brings me to the next part of the tutorial, depth refinement. And if you search, depth map refinement, this is a really hot topic. I mean, there's tons of research about this. There's also stuff specifically related to the Kinect. There's a paper here about it. So I just mentioned that to say, this is a huge topic. You could go really deep down this rabbit hole. I'm not saying that my solution here is the most sophisticated, but I do think it does a pretty good job for these sorts of issues. So before we jump in, I just want to give a little overview of the process here. I'm going to be addressing 3 different issues in this depth map. One is spatial noise. That's kind of the main issue, is this graininess and flickeriness. So that we need a denoising solution. I'm going to be using an algorithm called bilinear filtering, but there are other options there. The next one is also denoising these speckles on kind of the sides here. I'm going to use a speckle filter. And then finally, we have the holes that we want to fill in with a space filling algorithm. I'm going to use something that I'm calling nearest neighbor fill. So instead of taking the time to code all these things on the fly, I decided to just implement them and explain the code to you, because really the concepts are more important here. So the first step is this speckle filter. Here's without. You can see little speckles on the right here. And here's with. It's a pretty simple shader. I'm checking the 4 neighbors next to this pixel and then seeing how many of them are empty, meaning the alpha is 0. And if there are enough empty neighbors, I assume that it's a speckle and I get rid of it. The next one is hole filling. So here's without. You can see these black holes that show up, especially when I move my hand, and those are invalid pixels that the sensor can't read properly. Here's with. It's not perfect, but you're not seeing those black holes anymore. Here's the code for it. I'm basically just searching in rings around any invalid pixel until I find a valid neighbor, and then I replace it with the valid neighbor. A subtlety here is this second input. That's basically serves as a mask for what's inside or outside the body. If I get rid of this line of code, you'll see why I need that. There's no way to tell without this mask whether a pixel is on the inside or the outside of the shape and needs to be filled in. The way that I created this mask is a bit of a trick. If we go back into this Kinect component, I'm using the IR image from the Kinect to create this mask. I have found that it performs better under close conditions. You can see in this point cloud, there's black holes when I put my hand up close, but here it's totally white. So this is just a good tip to know if you ever want to create a good mask of the shape. It's helpful to use this IR image instead. This IR mask still isn't perfect sometimes, like you can see these black shapes here. So another thing I'm doing here is to blur it a little bit and then threshold it again. And that will kind of smooth it out and get rid of some of those black shapes. So this next step is smoothing. This is really the most important one, and it's the bilinear filter. Sort of the naive approach to this problem might be to just add a blur top and start to spatially blur the image. And that does create a smoother image, but it has issues. The edges of this object become strange because now you're combining pixels with very different depth values. So what we need is a new sort of blurring algorithm that will preserve edges. And this is a known issue, especially with depth maps. It's called edge preserving filters, edge preserving smoothing, and a pretty common algorithm to achieve that is bilinear filters. Here's without and here's with. So I'll show you the code for this. It's basically an advanced Gaussian filter where this is kind of the usual effect of a Gaussian filter. You compute a spatial weight based on the proximity to the pixel, and that creates a nice natural smooth blur that kind of fades out over distance. What the bilinear filter adds is this second weight called the range weight usually, and that's calculated based on the difference in depth. The important thing here is this U sigma R uniform. So if I open this up, it basically changes how sensitive the filter is to differences in depth. So when this is at 0, it's not going to combine any pixels because none of them are close enough in depth. As I move this up, it's going to combine more and more of the pixels until basically all of them are combined, and it's just a normal Gaussian blur. So I find that 0.1 is a pretty good value for this. The last thing I'm doing is using a noise top to just add a little bit of texture. So the period is 0, amplitude is 0.001. I think those are really the only two changes here. And alpha is set to input. Without that, you might get this weird background. But here's without that, and here's with. It's kind of a stylistic choice, but I just like the subtle texture that it adds. So you could take it or leave it. All right, there is one last thing here I want to address, which is this weird little edge here. And if you look, this is because of the normals. When you transition from the subject to the background, there's kind of this invalid pixel that shows up. The fix for that is going to be in this direct positions and normals talks. So I went ahead and rearranged this a little bit to give us some space. I'm going to create a new component here. Let's call it edge mask. And there's sort of a trick to just remove this last pixel, and that is to first threshold based on alpha. I'm going to add a little bit of blur and another threshold. I'm going to explain this in a bit. The last step is to take an inside here, plug in the depth, and use this instead. Okay, we haven't seen anything yet. If we go back into this edge mask, we change the second threshold to 1, and then we can adjust this blur size to maybe something like 2, something small. Now you'll see this little edge has disappeared, and I'll try to explain why. This combination of the blur and threshold operators are really handy. So you're taking the silhouette that has really hard lines from 0 to 1, and you're blurring a little bit, so there's some values, intermediate values there of like 0.5. So when you then threshold, you can basically cut into the shape. You get rid of those intermediate pixels that the blur created. And this allows you to really easily shrink a shape. It's kind of a lot of work and explanation for a pretty subtle thing, but I do think it makes a difference to not have that little edge there. So if we go back to our tutorial outline, that completes the depth refinement section. You know, there's more we could do. There's some cleanup here. It could be cropped a little bit, but I'm going to leave that there for now and go on to shadows. So we're going to go back into the direct rendering method. This render looks pretty good, but there is something very important missing here, which is shadows. In order to have a realistic scene, you need to have shadows. And you might think that, you know, maybe I could just turn this light on and say soft 2D mapped. This is not going to work, and that's because of how shadows are calculated in TouchDesigner. So I'm going to turn this off. They use what's called a shadow map. If you want to learn more about this, I would highly recommend checking out this Learn OpenGL page all about shadow mapping. But essentially what is happening is you're rendering the scene from the perspective of the light and getting a depth map. So if I plug this light into the depth top and look at a normalized split, this is the depth map of the light, right? And that's because it's just looking at a grid. There's no information here in the geometry about what we're trying to render. So when TouchDesigner goes to calculate the shadows based on this depth map, it's not going to work properly. I thought long and hard about this problem and tried to come up with a way to like calculate shadows just within the fragment shader without that depth map by like marching towards the light from each point. It didn't really work very well. So the solution that I came up with for shadows is to basically use the amazing shadows that we have with the instancing setup and combine it with the direct rendering. Because you're just using it for shadows, you can reduce the resolution a lot of the instancing and still have it pretty performant. So let's copy this instancing node and paste it into here. I'm going to call it shadows, and I'm going to select the position, plug that in here. We should have the same sort of instancing setup from above. And what we want to do is basically hook this up so that it's rendering the shadows from the same light that is being used to render this direct rendering method. First, I'm going to go in here in the render top. I'm going to select up one and do light one. Then in light one, we want to turn on shadows. I'm going to turn off the shadow strength for our custom GLSL material so you don't see that artifact of the grid sop. And let's change these as we did before. So I'm going to go to 0.1, max shadow strength I like at about 0.02. And really important, you need to change this shadow casters parameter to work with the geometry within shadows. So we can do shadows /star. And now in here, we should start to see a bit of a render. It's a little bit hard to see right now. Maybe what we can do is just for now, turn up this base color so you can see it a little clearer. One thing I'm noticing is that these shadows are getting cut off above the neck, and we can kind of debug that using this depth top. It's a really good idea whenever you're working with shadows to use this depth top with the normalized split so you can see what's in the view of the light. So I know that I need to adjust this a little bit, and we want to get it so that the instance geometry is filling most of this depth top, and the lighting of the direct method still looks good. So now if we come back in here, we should see that the shadows are looking pretty good and should be corresponding with this rendering setup. What we can do now is set up a secondary buffer to output just the shadow strength, and I'll show you how to do that. If you go to render, we need to go to the advanced page, increase this to 2, go to the PBR, go to advanced, set the color buffer parameter to shadow strength, and then we can create a render select, pass the render top in here, and change the index to 1. And now we're getting just the shadow strength output from the render. So if you're not familiar with using render buffers, there's a lot of cool stuff you can do with this. If you want to learn more, I highly recommend checking out this tutorial series from XDOS. Okay, so now that we've got this shadow strength, I don't really care about the actual render, but what I want to do is use a level top to invert this, and we'll use that as our output. Now, if we come back out here, we can maybe expand this out a bit, and I'm going to use a multiply to combine these two before we pass it into the bloom. Here's the basic idea, right? Like now we've got nice shadows that are working with the geometry. There's a few things to fix about it. It's still very expensive right now, but we've sort of combined the power of the shadows that are calculated for us when we are instancing with the power of this direct rendering method with really nice lighting based on normals. So let's clean this up a little bit. The first thing that I want to do is add a pre-shrink method here. So I'm going to customize, create a pre-shrink parameter, and let's set that default 1, max, let's go to 10 or something. I'm going to shrink this position based on that value. So I'm going to use a fit top and do me.inputs of 0.width over parent.par.pre-shrink. And let's do the same with height. Now we can change this pre-shrink, and we're probably going to get an error here. Because all ops must generate the same number of instances. This rope 2 we actually don't want for shadows, so I'm just going to get rid of that. And again, you'll notice these weird artifacts, and that is because we need to change the input smoothness to nearest pixel. That's going to get rid of a lot of that. Now the nice thing is that we can really shrink this quite a bit and still get decent looking shadows. We don't need the full resolution of this instancing setup. And something else we might want to do here is to add a little bit of blur to get rid of the grid. So, you could crank this up decently high and still have decent looking shadows here. There's another thing I want to do here, which is I'm going to get rid of this rotate 2. But now that they're not all rotated, we can actually adjust our shadows by increasing the depth of these little boxes to make it more of a full object. And I'll show you what I mean. If we go to this box, we need to set the anchor W to 1, and that's going to mean that we can scale up the Z axis and it'll just stretch out towards the back. And as we do this, the object is going to get more filled in basically, and it's going to create sort of nicer shadows. We are getting some weird grid artifacts, so maybe what we can do there is increase the point size a little bit, maybe even to like 2, and that's going to cut that out. We did kind of lose some detail there, so there's a fine balance to strike here. It seems like 1.5 is about good. I like to expose that as a parameter, so we could call that something like surface width and set that default to be something like 10. And we'll hook it up here as parent.par.surface width. And, maybe even something like 20 is good. Without that, the shadows look a little bit wishy-washy, and that kind of helps to make them more solid, right? That's kind of it. Now we have this customizable shadow component, and it will sync up with the lighting here. So if we want to change where this is oriented. The lighting for both the direct rendering and this instanced shadows should stay synced. All right, so I'm going to call this tutorial here. I'm pretty happy with this result we got. It's fairly performant. You've got interesting shading, you've got nice shadows, and there's lots to play around with here. You know, you could change parameters on this PBR material. You could adjust the lights that are present in the scene. I do also want to add that this idea of using direct rendering to render depth maps doesn't just apply to the Kinect. You could use this technique with any sort of depth map, whether that's from Kinect or from something like a generative feedback system. So this is a pretty powerful technique, and hopefully I'll be making more tutorials about how you can use it in other cases as well. I hope this tutorial was helpful. Hope you learned something, and thanks for watching.